This is Mrs. Basin, and today we're going to talk about solubility equilibria, which is section 17.4. So the last type of equilibrium we're going to look at is the equilibrium that exists when an ionic compound dissolves in water. So what we're looking at here is when you have an ionic compound and it dissolves, it breaks up into its component ions. So there's an equilibrium that exists when that happens between the solid and the ions, and that equilibrium is notated as KSP. So here's an example. So when we set this up, you can see this is for barium sulfate. So barium sulfate is given here, and you can see that dissociates into barium plus 2 and sulfate plus minus 2. So when you set up the equilibrium constant, it's still products over reactants, but notice now the reactant is not included because it's a solid. So the equilibrium expression would just be K equals Ba plus 2 SO4 minus 2. Okay, another example is this one here. This time you have 3 barium ions for every 2 phosphate ions. So now we're going to have to be a little more careful with the coefficients. Up to this point, most of the stuff we've been dealing with was 1-to-1, so now we're going to have to be careful again with that. So when you set up the KSP, again, it's products over reactants raised to the power of the coefficient. So this barium is raised to the 3rd power, phosphate is raised to the 2nd power. Okay, so let's look at an example. So this one says, write the expression for the solubility product constant, which is KSP. So when they're asking for that, that's KSP, for CaF2. So if I have CaF2, set up the equilibrium, I have calcium plus 2 plus 2F minus. So when I set up the KSP for this, it's going to be calcium plus 2 and then F minus to the 2nd. And again, the calcium, the original calcium fluoride is not included because it's a solid. Okay, so now when we're looking at this, KSP is not the same as solubility. So KSP looks at the rates of the forward and the reverse reaction. Solubility is how much of that substance will actually dissolve in water to make a saturated solution. So there's a couple common units for solubility. So as you're solving these problems, a lot of time the end goal will be to give the solubility either in moles per liter or in grams per liter. So this little map here kind of shows us how all those things are related. So you can see that you can go from the KSP to the molar concentration of ions. You can go from molar concentration to molar solubility. You can go from molar solubility to mass solubility, which is grams per liter. So we'll do lots of practice kind of interconverting between all of those. So let's look at how that's applied. So this one says we have solid silver chromate, and that is added to water at 25 degrees Celsius. And if you look at the solutions after they've reached equilibrium, it shows that the silver ion concentration is 1.3 times 10 to the negative 4. Our goal here is to calculate KSP. So what we need to do first is to set up our equilibrium expression. So silver chromate is Ag2 Cr04, and that dissociates into 2 silvers and 1 chromate. And again, this original compound comes from your ionic compound formation rules, where you're crisscrossing the charges and you set it up that way. Okay, so since our first substance is a solid, we're going to put lines through that because there's not going to be any values there because its concentration is not going to change. If they don't say this is dissolved in anything but water, those initial concentrations are going to be 0. Now the only information they're giving us here is the silver ion concentration. So that means at equilibrium, silver is 1.3 times 10 to the negative 4. Okay, we're going to go back to our rules where if they're giving us the equilibrium, then we can figure out the change. That means this increased by 1.3 times 10 to the negative 4. And then if we look at our stoichiometry, there's 2 silvers for every 1 chromate. So that means there's going to be half as much chromate being added as this reaches equilibrium. So that means for our chromate concentration, it's going to be 6.5 times 10 to the negative fifth. And then we can add that, 6.5 times 10 to the negative fifth. So then once we have that, now we can set up our K expression. So KSP equals AG plus to the second times CrO4 minus, and then we're going to substitute those values in, and I'm not going to show that substitution, but all I'm doing here is substituting these in, and then that gives me a KSP value of 1.1 times 10 to the negative 12. Okay, another version of this is it could ask you to find the molar solubility or the gram solubility. So this one gives us the KSP. So KSP for calcium fluoride is 3.9 times 10 to the negative 11. All of these things are temperature dependent. That's why they're giving you the temperature. Assume there's no temperature change unless they tell you otherwise. So it says, assuming that calcium fluoride completely dissociates upon dissolving and there's nothing else going on, calculate the solubility of CaF2 in grams per liter. So I'm going to start this one the same way, where I set up the CaF2. I show the dissociation. That becomes Ca plus 2 and 2F minus. My original solid is not going to change. My initial values are going to be 0 because it says I'm just dissolving it in water and there's nothing else going on there. Now this time they don't give me anything in equilibrium. What they give me is the KSP. So that means I'm going to go back and use my x's. So this one, calcium is going to increase by plus x. This again is where you have to be careful of those coefficients. The fluorine is going to increase by 2x. So then I have x times 2x, or I'm sorry, x, and then I'm adding the 2x there. So when I set up my KSP, I know KSP is 3.9 times 10 to the negative 11th, and that's going to be equal to my calcium, which is x, times my fluorine, which is 2x to the second. So up here, if I set up my KSP, just so you can see where that comes from, calcium plus 2, F minus to the second, and then what I'm doing there is I'm substituting the x in for calcium, the 2x for the F minus. So that's where all that comes from. So now I'm going to go through it. I'm going to solve for x. So I'm going to put that up here. So x equals 2.1 times 10 to the negative 4th molar. So what that gives me is the concentration of ions in solution. So if I want the concentration of calcium ions, it's equal to just x. If I want the concentration of fluorine ions, I have to take 2 times that x value. Now what this one is asking for is the solubility in grams per liter. So this is the solubility in molar, this is the molar solubility. What we have to do then is change the solubility to grams per liter. So I'm going to take this 2.1 times 10 to the negative 4 moles per liter, which is what that molarity is, and I'm going to convert it to molar mass in grams. So I'm going to use the molar mass of CaF2 because that's what they're asking for. So when I take the molar mass of that, it's 78.1 gram, and then per 1 mole. So then what that does is that changes the solubility from molarity to grams per liter. And when I do that, I get 1.6 times 10 to the negative 2 grams per liter. Now if you look at that number for just a minute, that's a really, really small value. So the solubility of most of these things that we're looking at is going to be very small. So this means that 1.6 times 10 to the negative 2 grams, which is a tiny, tiny amount, is all that will dissolve in 1 liter. So these things are not very soluble at all.